The decade following the First World War left Germany subjected to a system of military limitations aimed at preventing the reconstruction of its war capabilities. The provisions of the Treaty of Versailles reduced the army to dimensions incapable of sustaining large-scale operations and prohibited the development of military aircraft, heavy artillery, and technologically advanced weaponry. The restrictions directly affected scientific institutions and industries that had supported Germany's military capacity in the past. However, they also created a scenario in which experimental research, presented as academic or civil work, gained increasing importance as an alternative way to preserve technical knowledge and explore new fields with military potential. During the 1920s and early 1930s, the German scientific structure maintained a high level of specialization in physics, chemistry, metallurgy, and aviation. The universities of Göttingen, Berlin, Munich, and Heidelberg held international prestige, and companies like Krupp, Siemens, AEG, Junkers, and Messerschmitt operated with decades of experience. This environment facilitated the continuity of projects that, although officially oriented towards civil applications, allowed for the study of technologies that would later become pillars of advanced weaponry. The existence of teams capable of tackling complex engineering problems became a decisive advantage when the Nazi regime took power in 1933 and reorganized German research with strictly military criteria. From the rise of Adolf Hitler as Chancellor, the state took direct control over the scientific community. The reorganization was accelerated by the systematic expulsion of Jewish scientists from universities and institutes, a measure that produced an immediate loss of specialized talent, but at the same time ensured a homogeneous administrative framework for the regime. The Reich Ministry of Science, Education and Culture, led by Bernhard Rust since 1934, unified funding lines and directed academic centers and laboratories towards applied research programs. Private institutes and industrial companies were integrated into a centralized network that prioritized the engineering of new weapons systems. This concentration of resources allowed embryonic projects in rocketry, jet propulsion, special artillery, and nuclear physics to find political support and stable funding. One of the fields that received early impetus was that of liquid fuel rockets. During the 1920s, the development of rockets had been a marginal activity carried out by civilian groups of enthusiasts. The most influential was the Verein für Raumschifffahrt, founded in 1927, which conducted tests with small vehicles on the outskirts of Berlin. These experiments, although rudimentary, demonstrated that liquid propellants could produce controllable thrust. Among the young engineers involved was Werner von Braun, who joined the association in 1930 while preparing studies on rocket technology. His work caught the attention of Captain Walter Dornberger, an artillery department officer tasked with exploring alternative methods to overcome treaty restrictions. In 1932, the Army incorporated von Braun and several members of his group into the Kummersdorf facilities, where they began working under military supervision. The objective was to assess the potential of rockets as long-range artillery. The first vehicles, designated Aggregate 1 and Aggregate 2, reached heights over 2 kilometers in 1934, using diluted ethanol as fuel and liquid oxygen as an oxidizer. These prototypes introduced elements that would become essential in later projects: combustion chambers designed to withstand high pressures, gyro stabilization systems, and lightweight structures manufactured with strict tolerances. The technical difficulties, unstable combustion, feed pump failures, and structural deformations demonstrated the complexity of the task, but the results were sufficient to justify the expansion of the program. Kummersdorf proved insufficient for continuing with larger rockets. Space limitations and proximity to populated areas prevented safe testing. Therefore, in 1936, the Army selected Peenemünde on the Baltic coast as the new development center. The location allowed launches over the sea and the construction of extensive facilities in an isolated environment. The construction of the complex began in 1937 and included manufacturing workshops, laboratories, liquid oxygen production plants, wind tunnels, and test platforms. Peenemünde was conceived as a comprehensive centre capable of housing thousands of technicians and scientists. The first design produced there in its entirety, the Aggregate 3, introduced aerodynamic and structural principles that defined the future trajectory of German rocketry. Although its tests in 1937 and 1938 showed frequent failures, the program advanced rapidly and consolidated an indispensable technical base for subsequent developments. As the research on rockets progressed, the regime promoted a second field of great potential: jet engines. The idea of propelling aircraft by expelling gases at high speed had been studied theoretically, but in the 30s, the first tangible developments began. Hans von Ohain, a young physicist, proposed a design based on the compression of atmospheric air mixed with fuel and its continuous combustion in a chamber where the gases expanded through a nozzle. The first demonstrators built by von Ohain in 1935 operated briefly before failing due to thermal problems, but they demonstrated the viability of the concept. Ernst Heinkel, owner of one of the country's main aeronautical companies, recognized the potential of this technology and provided von Ohain resources to develop a complete engine. The result was the HES-3, which produced around 500 kilograms of thrust. This engine was installed in the Heinkel He 178, an experimental aircraft that made its first flight on the 27th of August, 1939. The pilot Erich Warsitz kept the aircraft in flight for several minutes, demonstrating the possibility of operating an aircraft without propellers or conventional engines. Although the fuel consumption was high and the engine's durability was limited, the flight constituted a technological milestone that confirmed the potential of jet propulsion. In parallel, Junkers was developing an alternative project under the direction of Anselm Franz. The future Jumo 004 engine adopted an axial design that allowed for improved efficiency by compressing the air through a series of longitudinally aligned stages. This approach had greater potential for military applications, as it offered better performance characteristics and the possibility of generating higher thrusts. The engine was still in its initial phases in the late 1930s, but it laid the foundations of what would later become the first mass-produced jet engine. The regime also supported experiments in special artillery with the aim of achieving ranges far superior to those of conventional cannons. Engineers studied multi-chamber configurations, where auxiliary charges ignited sequentially as the projectile passed, devices that generated shock waves to affect aircraft at close range, and rocket projectiles launched from cannons that used their own engines during flight. These investigations took place in Hillersleben, an establishment experienced in artillery testing. The prototypes worked in a limited manner with synchronization problems, premature material erosion, and structural failures. None of these lines advanced beyond experimentation, but they provided relevant data for subsequent long-range projects. The most recent field with the greatest potential impact was nuclear physics. At the end of 1938, Otto Hahn and Fritz Strassmann identified unexpected products when bombarding uranium with neutrons, observing the presence of lighter elements. Lisa Meitner and Otto Frisch provided the correct theoretical interpretation of the phenomenon: the splitting of the uranium nucleus into smaller fragments, accompanied by the release of large amounts of energy and additional neutrons. The possibility of a chain reaction opened up technological scenarios ranging from controlled reactors to explosives of previously inconceivable power. The discovery was quickly published in January of 1939 and triggered immediate analysis among physicists from various countries, including Germany, where the first studies on the feasibility of controlling chain reactions began shortly after. By the time September of 1939 arrived, Germany had fundamental technologies in their initial phases: rockets capable of reaching significant altitudes, jet engines that had proven their utility in flight, and a newly acquired theoretical knowledge about nuclear fission. None of these advancements were ready for immediate military applications, but all had considerable potential that the regime would recognize at the start of the war, when strategic pressure would drive the transition of these experiments into projects with defined military objectives. The beginning of the Poland campaign on the 1st of September 1939 reinforced in the German High Command the conviction that the combination of armored forces, immediate air support, and continuous operations could destabilize much more extensive defenses in brief spans. The fall of Warsaw in a little more than 1 month was followed by equally rapid operations in Denmark, Norway, Belgium, the Netherlands, and France. By June of 1940, the strategic balance in Europe had changed abruptly. Germany controlled extensive industrial areas, key ports, energy resources, and a railway network that allowed moving personnel and materials efficiently. This new scenario facilitated allocating resources to technological programs that, until then, were experimental initiatives without an immediate application forecast. The German military apparatus began to evaluate which projects could offer concrete advantages if developed with priority. In Peenemünde, the rocket program entered a phase of accelerated expansion. The Aggregate 4, conceived from the beginning as a complete weapons system and not just as an experimental vehicle, represented the next logical step after the initial results of the 1930s. The preliminary specification defined a rocket 14 meters in length, 12.5 tons in total weight, and an engine capable of generating about 25 tons of thrust for a little more than 1 minute. With fuel based on diluted ethanol and liquid oxygen, the structure had to withstand internal pressures of up to 15 atmospheres and temperatures exceeding 2,700 degrees Celsius. The complexity of this system required integrating into a single vehicle elements that had never before operated together in a device of this size: high-performance turbo pumps, internal control surfaces made of graphite, precision gyroscopes, and a lightweight fuselage resistant to extreme thermal fluctuations. The development progressed through continuous cycles of testing and analysis. The combustion chambers had to maintain a stable mixture of fuel and oxidizer, which led to the design of an injector composed of more than 1,000 holes that distributed the liquids in calculated patterns to minimize oscillations. The turbopumps, activated by vapor from catalytically decomposed hydrogen peroxide, operated at more than 4,000 revolutions per minute while pumping cryogenic liquids. Problems arising from the contact between materials subjected to extreme temperatures and constant vibrations were frequent. Even so, each failure provided useful data to adjust internal geometries, modify cooling channels, or recalibrate orientation sensors. The preparation of the flight tests also required building auxiliary infrastructure for mobile operations. The Milowagen platform was developed, designed to transport, elevate, and prepare the rocket in improvised launch areas, reducing the need for fixed installations susceptible to aerial reconnaissance. This system indicated that, even before achieving a fully reliable prototype, the method of use in a real operational scenario was being planned. The tests conducted in 1942 reflected the degree of technological difficulty. The launch attempt on the 13th of June ended after a few seconds due to an engine feed failure. The second test on the 16th of August ended in the destruction of the vehicle in mid-flight after a fuel leak. Success came on the 3rd of October, when the rocket reached an altitude greater than 80 kilometers, traveled around 190 kilometers, and demonstrated the validity of the theoretical calculations. Although subsequent launches revealed additional failures in pumps, pressure accumulators, valves and structures, the October flight marked a turning point. The political leadership ordered an increase in personnel, the expansion of facilities, and the preparation of production lines aimed at manufacturing the rocket in significant quantities. The program shifted from being advanced research to a strategic project. Meanwhile, advances in jet propulsion offered potential to transform the capabilities of military aviation. The experimental flight of the Heinkel, He-178 in 1939, had demonstrated that a jet engine worked under real conditions, but its performance was insufficient for operational applications. The next step was represented by the development of the Me-262 by Messerschmitt. This aircraft integrated two Junkers, UMO 004 turbojets, mounted under the wings, and an aerodynamic structure designed to reach speeds far superior to those of propeller planes. The UMO 004 engine was a complex system. The 8-stage axial compressor compressed air to several atmospheres before directing it to 6 tubular combustion chambers. The hot gases drove a single-stage turbine that powered the compressor. The choice of an axial compressor allowed for greater efficiency and less frontal resistance, but required extremely precise alignment. One of the biggest obstacles was the lack of nickel alloys needed to manufacture turbine blades capable of operating for an extended period at high temperatures. Germany relied heavily on imports of strategic materials, which forced its engineers to develop steels with chromium and molybdenum that operated within a limited threshold. The lifespan of the engine was a few dozen hours, but enough to demonstrate the operational feasibility of the design. The Me-262 made preliminary flights in 1941, equipped with a provisional piston engine, used to validate the stability and aerodynamic responses of the fuselage. The first flights completely powered by the two turbojets began in July of 1942, and the results confirmed that the speed and climb capability far exceeded those of contemporary fighters. However, the development still faced technical difficulties, such as vibrations at high speed, additional stresses on the wing structure, and recurrent failures in engines subjected to abrupt acceleration cycles. These aspects would require continuous modifications during the following months. In the naval field, the results obtained in the first years of the war indicated that conventional submarines were reaching the limit of their capabilities. The U-boats had sunk large amounts of merchant tonnage between 1939 and 1941, but their reliance on surface navigation to recharge batteries made them vulnerable to the increasing use of radar and patrol aircraft. The need for a radically different design led to preliminary studies that would define the general lines of the future Type 21. Although its full development would not begin until 1943, between 1939 and 1942, the essential technical principles were established. A hydrodynamic hull to operate mainly submerged, high-capacity batteries, electric motors sized for long underwater voyages, and a snorkel capable of supplying the diesels at periscope depth. These conceptual advances anticipated a new generation of submarines designed for an operational reversal of existing doctrine. The German nuclear program also evolved during this period. The occupation of Norway provided access to the Vemork heavy water plant, whose product was essential for the moderation experiments needed in a nuclear reactor. From 1940, production was increased by installing new stages of electrolysis and concentration. In parallel, the team led by Werner Heisenberg tested different geometric configurations of uranium and heavy water to measure neutron multiplication. Between 1940 and 1942, tests were conducted with spherical, cylindrical, and alternating layer designs. The results confirmed that the chain reaction was close to occurring, but the loss of neutrons and the insufficient purity of uranium prevented reaching criticality. Estimates indicated that several tons of metallic uranium and a similar amount of heavy water would be necessary to achieve this, resources that exceeded the immediate production capacity. Nevertheless, the theoretical advancement provided a clear foundation for subsequent experiments. Simultaneously, the High Command evaluated the need to have bombers capable of operating at intercontinental ranges. The possibility of reaching the east coast of the United States from European bases required aircraft with capabilities that far exceeded the existing ones. The preliminary requirements of the America bomber demanded a total range of more than 10,000 kilometers, the ability to carry a significant load, specialized navigation systems, and high-efficiency engines. Various companies presented conceptual proposals. The Messerschmitt May 264, the Junkers Ju 390, the Horton Ho 18, and the rocket-assisted project of Eugen Sänger. None of these designs were ready for construction, and all depended on technological advances that did not yet exist, but defined lines of research that would continue during the following years. By the end of 1942, Germany had transformed experimental projects into development programs with defined military objectives: large-scale rockets, jet aircraft, submarines optimized for submerged navigation, experimental nuclear reactors, and long-range bombers had surpassed the initial phase. Although none were ready for mass production, their technical foundations were already established. The change in the course of the war, starting in 1942, would turn these initiatives into growing priorities, accelerating their schedules and serving as the basis for the decisive advances that would characterize the following period. At the beginning of 1943, Germany's strategic situation had changed significantly. The surrender of the Sixth Army in Stalingrad on the 2nd of February confirmed that the Eastern Campaign had turned into a prolonged war where the adversary possessed far superior industrial resources and manpower reserves. The fall of the German defences in North Africa, culminating with the surrender of all Axis forces in May of 1943, added additional pressure on the German military structure. The strategy based on quick campaigns had given way to a conflict where production, logistics, and engineering became decisive factors. In this new scenario, advanced weapons programs gained increasing importance. Projects that for years had been technical experiments now had to become functional systems capable of influencing the development of the war. The V2 rocket program in Peenemünde was one of those facing the greatest expectations. Since the partial success achieved in October of 1942, engineers had been dedicated to solving problems that conditioned the transition from the prototype to an operational weapon. Combustion stability continued to be a fundamental technical challenge. Internal oscillations generated within the chamber could increase local pressures to critical levels, causing deformations or ruptures in a matter of milliseconds. To face it, multiple variants of the injection system were manufactured, modifying distribution patterns, the diameter of the orifices, and internal materials. Each version involved new tests, residue analysis, and detailed measurements of temperature and vibration. The turbopumps, responsible for supplying the combustion chamber with ethanol and liquid oxygen, also had recurring failures. The seals and bearings degraded quickly when operating with cryogenic liquids and under high dynamic loads. In several tests, small leaks had caused the accidental mixing of fuel and oxidizer inside the pump compartment, resulting in fires or explosions that destroyed the vehicle in seconds. To mitigate these risks, sealing systems were reinforced, axial supports were redesigned, and coatings were experimented with to reduce internal friction. The guidance system required equivalent improvements. The gyroscopes tended to drift, especially on prolonged flights, which produced significant deviations from the programmed trajectory. Engineers introduced reinforced supports, more stable rotors, and damping systems to reduce vibrations that altered the reading of the instruments. The graphite paddles installed within the engine jet, essential for applying trajectory corrections, suffered accelerated erosion at temperatures above 2000 degrees Celsius. Grades of graphite with different density were tested, and aerodynamic profiles were adjusted to prolong their lifespan. The structure of the rocket also underwent alterations. The fuel and oxidizer tanks acted as structural elements, which reduced weight but required strict tolerances. The walls of the tanks, with minimal thickness, were vulnerable when the vehicle was empty. Therefore, preparation procedures required immediate filling before launch to avoid deformations. Longitudinal reinforcements were adjusted, and welded joints were reviewed to reduce possibilities of fracture during the supersonic phase of flight. By March of 1943, the design was considered advanced enough to begin industrial planning. Each rocket contained around 30,000 individual components, and its manufacturing required highly skilled welders, precision machining equipment, facilities to handle liquid oxygen, laboratories to adjust guide electronics, and workshops to calibrate pumps and valves. Initial estimates indicated that it would be necessary to reorganize entire factories to sustain continuous production. The program already employed more than 15,000 people in Peenemünde, among engineers, technicians, military personnel, and civilian workers. In parallel, the development of the Me-262 jet aircraft showed significant progress, although accompanied by persistent difficulties. The Junkers Jumo 004 engines continued to be the main obstacle. The tests showed that the lifespan of these units remained limited to a few dozen hours, with frequent failures in turbine blades subjected to extreme thermal and centrifugal stress. The limitations in access to nickel and cobalt alloys forced the use of less resistant alternatives, which required constant adjustments in geometry, coatings, and cooling processes. The production of each engine demanded complex heat treatments and rigorous quality controls to detect microfractures invisible to the naked eye. The aerodynamic design of the Me-262 also continued to be refined. The speeds reached during the tests far exceeded those of conventional fighters, generating aerodynamic phenomena little known at the time, such as the accumulation of shock waves in specific sections of the wings or structural vibrations that appeared in high-speed maneuvers. Engineers incorporated reinforcements in critical points, revised leading-edge profiles, and adjusted movable surfaces to improve stability. The landing gear, initially undersized for an aircraft of these capabilities, was redesigned to withstand landings at higher speeds and more elevated load conditions. At the same time, the debate about its operational role continued. Hitler's insistence on using it as a fast bomber required structural modifications to carry offensive armament, including external bomb racks and specific release systems. Luftwaffe officers pointed out that these changes reduced the aircraft's efficiency as an interceptor, which was the role for which it had been designed. Training units also faced challenges. Pilots accustomed to piston engines needed to learn to manage less immediate accelerations, much higher speeds, and emergency procedures specific to jet engines. The training process was slow and absorbed additional resources. The development of the Type WW2 submarine, although it had not yet entered production, was advancing from concept to detailed engineering. This design represented a profound change in naval doctrine. For the first time, a submarine was conceived to operate almost continuously underwater. Extensive hydrodynamic tests were conducted in specialized tanks to optimize the shape of the hull, reducing resistance and increasing propulsion efficiency. The battery system, which doubled or tripled the capacity of previous models, required revising the submarine's internal layout and modifying ventilation and cooling systems to avoid accumulations of dangerous gases. The incorporation of the snorkel transformed the way of operating. Although the previous models could submerge, they had to surface frequently to recharge batteries, which made them vulnerable. The snorkel allowed diesel engines to operate at periscope depth, reducing exposure and increasing underwater autonomy. The engineers also designed a hydraulic torpedo recharging system that accelerated attack cycles. The tests conducted on test benches confirmed that the system could recharge 6 tubes in less than half an hour, a significant improvement compared to previous submarines. The German nuclear program underwent a similar expansion. The experiments in Leipzig had demonstrated neutron multiplication, but not criticality. Physicists identified that the purity of the materials was fundamental. Metallic uranium had to be manufactured with extremely high purity, free from impurities that absorbed neutrons. The production of metallic uranium required chemical facilities capable of handling highly corrosive compounds. The process started with crushed ore, followed by conversion to uranium tetrafluoride, and finally to metallic uranium through chemical reduction. Each phase needed specialized equipment to control intense exothermic reactions. The availability of heavy water remained the limiting factor. Although the VMORC plant had increased production, the estimated demand for a functional reactor exceeded the annual capacity. The German physicists accepted that reaching criticality would take several years, even with prioritized resources. Meanwhile, additional studies were conducted on isotopic separation, but the available techniques, thermal diffusion, centrifugation, and gaseous diffusion, offered marginal results and consumed large amounts of electricity. None of these methods advanced beyond experimental laboratory phases. In 1943, the High Command also continued examining possibilities of developing long-range aerial platforms. The idea of the America bomber was still in the theoretical phase, but some manufacturers conducted tests with scale models to assess aerodynamic profiles, weight distribution, and consumption estimates. The studies confirmed that it was necessary to develop much more efficient engines to make a round-trip transatlantic flight viable. Without these advancements, the projects remained as conceptual designs with potential, but without immediate possibility of construction. As these programs progressed, the V2 program faced its most critical test in August of 1943, when the Royal Air Force executed Operation Hydra. Around 600 bombers attacked Peenemünde during the night of the 17th to the 18th of August, dropping tons of explosives and incendiaries over assembly areas, dormitories, laboratories, and test stands. The attack caused considerable damage to essential structures and resulted in the death of technical personnel, including Walter Thiel, a key figure in engine development. Engine testing experienced temporary interruptions due to damage to test benches and supply systems. Even so, the main technical documentation survived, along with the majority of the key equipment. The bombing led to a reassessment of the site's security. The facilities at Peenemünde were too vulnerable to sustain large-scale production. In response, it was decided to move the manufacturing to underground facilities where Allied bombers could not reach them. This decision would initiate a reorganization process that would profoundly transform the program and mark the next period of the war, in which manufacturing in underground caverns, tunnels, and fortified complexes would become a central element to preserve the continuity of strategic programs. The bombing of Peenemünde in August of 1943 forced the German High Command to completely reorganize the production of advanced weapons. The attack had shown that even high-priority facilities, located in remote areas and protected by anti-aircraft defenses, were vulnerable to carefully planned bombing operations. Albert Speer, armament minister, had been evaluating for months the possibility of moving the manufacture of critical systems to underground facilities that could not be destroyed from the air. The blow received at Peenemünde accelerated the transition of these plans to immediate executive orders. Shortly after the attack, Speer established that the mass production of the V2 rocket would not continue on the surface under any circumstances. The site selected for this new phase of the program was located in the Harz Mountains, near Nordhausen, in the center of Germany. There were tunnels originally excavated to store fuel, whose basic structure allowed for rapid expansions. The place would form the nucleus of an underground industrial complex designated Mittelwerk. The choice was due to several factors: geographic isolation, proximity to railway lines, and availability of geological formations that allowed relatively rapid excavation. However, the initial conditions were far from ideal for a modern industrial facility. The tunnels required structural reinforcement, significant expansion, and ventilation systems capable of maintaining minimal working conditions for thousands of workers. The construction of Mittelwerk became an accelerated engineering project. The two main galleries, each almost 2 kilometers in length, were widened to reach dimensions close to 10 meters wide by 8 high. The transverse galleries, which connected the two main ones at regular intervals, functioned as assembly segments, storage areas, mechanical workshops, and inspection stations. The electrical system was expanded to supply continuous lighting and heavy machinery. The internal railway tracks allowed engines, fuselages, and pre-assembled sections to be quickly transported between stations. The installation of overhead cranes at strategic points facilitated the movement of components that could weigh hundreds of kilograms. The labor used for this vast project came mostly from the Mittelbau-Dora concentration camp, specifically created to provide forced workers. Thousands of prisoners, from camps spread across all of occupied Europe, worked continuous 12-hour shifts in environments with poor ventilation, constant anhydrite rock dust, and unstable temperatures. Lacking adequate facilities for accommodation and rest, the prisoners initially slept in the same tunnels where they worked. The conditions, combined with insufficient food and regular punishments, led to an extremely high mortality rate. Subsequent records estimate that more than 20,000 prisoners died during the construction and initial operation of the complex, a figure higher than the total victims later caused by the V2 rockets used in combat. Despite the extreme conditions, production began in a remarkably short period. In December of 1943, just a few months after the start of the project, the first assembly lines were operational. These lines operated sequentially, mimicking the structure of a conventional industrial plant, but adapted to the underground environment. The components of the V2 came from different parts of the Reich: engines from Reichswerke, tanks from aeronautical companies, electrical and guidance systems from firms like Siemens, valves and pumps from specialized manufacturers. All these elements were inspected upon arrival and distributed to the galleries where the final assembly was carried out. The manufacturing process of a V2 included thousands of individual operations. The main structure was assembled first, securing the cylindrical fuselage and the compartments for ethanol and liquid oxygen tanks. Next, the liquid combustion engine, the most complex assembly of the vehicle, was installed, requiring the assembly of injectors, steam-driven pumps, and combustion chambers cooled by pre-fuel circulation. The guidance system, based on mechanical gyroscopes and servo motors that managed the internal jet vanes, was added in later stages. Finally, the electrical wiring was connected, the exterior control surfaces were assembled, and the explosive warhead was installed. The initial production was irregular. In January of 1944, around 50 rockets were completed, a figure well below the projected number. Problems in the supply of components, assembly errors, and failures in quality control systems caused continuous delays. However, the work lines were progressively optimized through the standardization of procedures and the training of specialized German workers who supervised the forced teams. By March, production rose to more than 170 units per month. In June, Mittelwerk reached a production of more than 400 rockets per month, approaching the levels required for future operations. As the V2 advanced towards mass production, another retaliation system, the V1, reached operational maturity. The weapon, officially known as the Fieseler Phi 103, represented a different approach to ballistic rocketry. It was a primitive cruise missile, manufactured in large quantities and powered by an extremely simple pulse jet engine. This engine consisted of a metal tube equipped with reed valves at the inlet that opened to allow air intake, closed with combustion pressure, and repeated the cycle dozens of times per second. The simplicity of the design allowed for rapid production using conventional manufacturing techniques. The V1 guidance system combined gyroscopes to maintain stability, a magnetic compass to determine heading, and a mechanical counter powered by a small front propeller that estimated the distance traveled. When the counter reached a preset value, the mechanism activated the control surfaces to make the device dive. The accuracy was limited, with dispersions of several kilometers, but sufficient to attack extensive urban areas. The manufacturing of the V1 benefited from its simplicity. In 1944, more than 30,000 units were produced, a figure made possible by the use of common steel, standard welding techniques, and modular assembly. The V1 launch sites were established on the coast of the English Channel. These facilities consisted of inclined ramps that used booster rockets to bring the V1 into firing conditions. The first operational attack took place on the night of the 12th to the 13th of June of 1944. During the following months, large quantities of V1s were launched against England, especially against London. Although British defences increased their effectiveness by using fast fighters, anti-aircraft artillery with proximity fuses, and barrage balloons, the weapon managed to cause significant damage in urban areas and divert considerable resources from the main Allied effort on the continent. The production of the Me-262 jet aircraft also progressed during this period, although it faced persistent challenges. The concept of the aircraft had been defined years earlier, but the Junkers Jumo 004 engines continued to be the main obstacle. Their operational lifespan was extremely limited due to thermal stresses and lack of suitable materials. Despite this, the basic structure of the Me-262 was refined, and its speed superior to that of conventional Allied fighters granted it considerable potential. Allied bombings complicated manufacturing. The Messerschmitt plants and Junkers facilities were repeatedly attacked, forcing production to be dispersed into small factories and makeshift workshops. Pilot training also represented a considerable problem. Flying a jet aircraft required understanding that the engine response was slower than that of a piston engine, and that the speeds reached drastically reduced the reaction time available during maneuvers. Additionally, fuel consumption was high, and Germany's synthetic fuel reserves were dwindling due to Allied attacks on hydrogenation plants. These combined factors produced a situation in which, although Me-262 production increased, relatively few aircraft effectively entered operational service. In September of 1944, the first unit equipped with Me-262 was organized, but it had few aircraft and faced difficulties in sustaining continuous operations. The Type 21 submarine program continued to develop through the modular system introduced by Speer. The prefabricated sections were assembled in shipyards equipped with high-capacity cranes. This method reduced the total construction time to approximately 6 months. Unlike previous submarines, the Type 21 was designed to navigate primarily submerged, with an optimized hydrodynamic hull and high-capacity batteries. Initial tests showed submerged speeds exceeding 17 knots and underwater endurance of several days. However, numerous technical problems arose during the initial tests, including failures in electrical systems, problems in diesel engines, and defects in navigation systems. Although improvements were gradually incorporated into later units, none of the submarines achieved full operational capability during 1944. Furthermore, several land projects reached the prototype stage during this same period. The super heavy tank Panzer VIII Maus represented an attempt to create a heavily armored vehicle capable of dominating any ground confrontation. With its exceptionally thick armor and its main armament of 128 mm, the Maus surpassed any Allied tank in firepower and protection. However, its extreme weight limited its mobility, reduced its speed, and made it impossible to cross most existing bridges. Only 2 prototypes were completed without reaching operational service. Another significant project was the V3 Super Range Cannon, based on a multi-chamber design where additional charges accelerated the projectile along a fixed barrel. The complex built at Mimoyekes included multiple tubes arranged in parallel, protected by reinforced concrete structures. Although the theoretical design was viable, the site was identified by aerial reconnaissance and bombed in July of 1944 by bombers equipped with tallboy penetrating bombs. The destruction of tunnels and propellant chambers left the project inoperable before reaching operational capacity. By the end of 1944, Germany had managed to bring several advanced projects from experimental phases to states that could be considered operational or close to operation. The V1 was widely used, the V2 was being mass-produced underground, the Me-262 was gradually entering service despite critical limitations, and Type 21 was approaching final evaluation states. However, all these systems faced limitations arising from both technical problems and the constant pressure of Allied bombing and the increasing scarcity of resources. As the war advanced towards 1945, the real impact that these weapons would have on the battlefield would depend on their effective deployment in an environment where Germany's ability to sustain operations was rapidly diminishing. The operational use of the V2 rocket began on the 6th of September 1944, with a launch against Paris from a mobile position near Houffalize in Belgium. The projectile hit Maison-Alfort and caused 6 deaths, initiating a campaign that would change the nature of strategic bombing. 2 days later, on the 8th of September, the first attacks against London were carried out. At 1840, a V2 impacted in Chiswick, creating a crater of 10 meters and killing 3 people. Another fell minutes later near Epping. The total absence of warning distinguished the V2 from any previous weapon. It traveled at supersonic speed during the entire descent, and the sonic boom arrived simultaneously with the explosion, eliminating any possibility of prior shelter. The British government initially tried to conceal the ballistic nature of the impacts, attributing them to accidental gas detonations. However, the intensity of the pattern of destruction made this explanation unsustainable. By November of 1944, Churchill publicly acknowledged that London was being attacked with ballistic rockets. Between September of 1944 and March of 1945, German units launched approximately 1,400 V2s against London and 1,664 against Antwerp, whose port was essential for supplying Allied armies in their advance towards Germany. Other targets, including Norwich, Ipswich and Lille, received around 160 additional impacts. The launch rate fluctuated depending on the availability of rockets, fuel, and mobility conditions in the Netherlands and Belgium, but remained constant until the Allied advance forced the launch units to retreat. The human impact of the V2 was considerable. In London, 2,754 people died, and approximately 6,500 were seriously injured. In Antwerp, the victims exceeded 1,700, many of them dock workers and military personnel assigned to logistical operations. Although the material destruction was extensive, the strategic military effect was limited. The 1,000-kilogram warhead was destructive, but the accuracy of the V2 did not allow for selective military value attacks. Typical impact errors reached several kilometers due to intrinsic limitations of the gyroscopic guidance system, atmospheric variations, and slight irregularities in combustion and thrust. Each rocket was a single-use weapon and required a considerable investment of time, personnel, and materials for its production. By contrast, a single Allied heavy bomber attack could carry several times more explosive load in a single night mission. Conventional defenses were useless against the V2. Neither fighters nor anti-aircraft artillery could intercept a projectile descending at more than 5,000 kilometers per hour from altitudes close to 90 kilometers. The only viable countermeasure was the ground advance to capture the launch areas. This strategy worked gradually. By March of 1945, the positions still capable of reaching England were out of operational range due to the withdrawal of German forces. Consequently, the V2 campaign ended, not due to a lack of rockets, but because of the loss of suitable territories for launching. In parallel, the V1 campaign continued from June of 1944. Over 9 months, approximately 10,000 units were launched against England. The V1, propelled by a pulse jet engine, flew at a relatively low altitude and constant speed. These features allowed the British to organize a layered defensive system. Fast fighters like the Hawker Tempest and the Spitfire 14 formed an advanced line over the Channel, followed by about 2,000 anti-aircraft guns with proximity fuses and a barrage of captive balloons. The results became quickly evident. In June of 1944, around 40% of the V1s reached the target area. By August, the proportion had fallen to 20%. By the end of the year, more than 80% were destroyed before impact. Despite this effective defense, the V1 that managed to get through still produced significant casualties, causing about 6,184 deaths. The weapon fulfilled its tactical function to saturate defenses, force the redistribution of resources, and maintain constant pressure on the Allied rear, although it did not alter the general course of the war. In the air, the Me-262 began to enter combat in appreciable numbers at the end of 1944. After years of technical delays and conflicting decisions on its operational role, the Luftwaffe finally integrated the aircraft into specialized units. Commando Nowotny began operations in October of 1944, carrying out attacks against formations of United States bombers. The performance was remarkable, speeds that easily surpassed Allied fighters and a superior climbing capability. However, these advantages brought new difficulties. The extreme speed reduced the time available to aim. Approaching at 800 km/h to dense formations of bombers left just seconds to fire the 4 Mk 108-30 mm cannons, whose explosive projectiles could destroy a bomber with a few hits. The Me-262 required specific tactics, generally descending frontal attacks where the exposure time to enemy gunners was minimal. Even so, its strategic impact was limited. By February of 1945, there were around 200 operational Me-262s, an insufficient number to counter the thousands of aircraft deployed by the Allied forces. In addition, the vulnerability of the Me-262 during takeoff and landing represented a significant disadvantage. The slow acceleration of the Jumo 004 engines and the need for long runways allowed Allied fighters patrolling over known bases to detect and destroy jet aircraft before they managed to climb to a safe speed. Adding to this was the chronic shortage of fuel, aggravated by Allied bombings against synthetic fuel plants. Many Me-262s remained grounded due to lack of fuel or damaged engines that could not be replaced quickly. The Arado R-234 Blitz, the first operational jet bomber, also entered service in this period. Although its performance was outstanding, speeds exceeding 740 km per hour, the total production of about 210 units severely limited its impact. The R-234 carried out long-range reconnaissance missions and selective attacks, especially against Allied bridges over the Rhine, but its small number prevented it from significantly influencing strategic operations. Other advanced designs arrived late or with insurmountable problems. The Heinkel He-162, conceived as a light fighter for accelerated production, exhibited dangerous flight characteristics and control difficulties, with multiple accidents recorded during tests. Although approximately 120 units were manufactured, only a few reached operational missions with no significant results. The Messerschmitt Me-163 Comet, powered by a short-duration rocket engine, could reach speeds over 950 km/h and quickly ascend to high altitudes, but its limited range, high operational risk, and extreme volatility of its fuel made it an impractical system. Despite manufacturing about 370 units, its confirmed shootdowns were scarce, and the losses due to accidents numerous. In the sea, the Type 21 submarines, designed to operate submerged for long periods thanks to high-capacity batteries and optimized hydrodynamic hull, did not enter full operation before the end of the war. Although more than 100 units were launched between 1944 and 1945, technical problems and training delays prevented them from being deployed on effective combat patrols. The U-2511, the first Type 21 declared operational, conducted a test patrol in April 1945 that demonstrated the design's ability to evade Allied anti-submarine forces more effectively than previous models. However, the end of the war came before it could conduct real attacks. Later, Allied analyses confirmed that the design represented a considerable technological leap, capable of altering submarine warfare if it had been available in 1944. The German nuclear program also did not reach military applications. In 1944 and 1945, the facilities were dispersed to avoid bombings. The most advanced experiment, the B-8 reactor in Haigerloch, consisted of 664 cubes of metallic uranium suspended in a heavy water solution. Tests conducted in the first months of 1945 showed significant neutron multiplication, but not criticality. The project lacked enough heavy water and metallic uranium of the required purity. The capture of the facility by the American Alsos team on the 23rd of April 1945 marked the effective end of the German nuclear effort. At the beginning of 1945, the military situation of the Reich was rapidly deteriorating. The Allied advance toward the heart of Germany was cutting supply lines, capturing manufacturing facilities, and reducing the ability to operate advanced weapons. The last V-2 rockets were launched in March from positions in the Netherlands before being abandoned. The production of the Me-262 decreased as factories were occupied. The Type 21 submarines were left in shipyards or made brief sorties without operational impact. The nuclear project was left isolated and without resources. When Germany surrendered on the 7th of May, 1945, the advanced weapons of the regime had demonstrated remarkable capabilities, but lacked the time, resources, and operational context necessary to significantly alter the final course of the war. When the Allied armies entered Germany during the early weeks of 1945, they advanced with specialized units whose mission went far beyond conventional military operations. These were technical scientific teams tasked with identifying, evaluating, and securing advanced German technologies before they could be destroyed by retreat orders or fall under the control of another power. Allied cooperation existed only in appearance. At the operational level, the United States, the United Kingdom, and the Soviet Union competed directly to gain strategic advantages that would influence the military and technological structure of the post-war period. The end of the Third Reich became, within weeks, the practical beginning of the Cold War. In this context, the United States launched what would become the most extensive scientific capture operation of the time, Operation Paperclip. Although its formal approval came in August 1945, lists of German engineers, physicists, chemists, and technicians considered essential were already being compiled from the beginning of that year. The candidates' files were marked with a paperclip, the origin of the operation's name. Its real objective, beyond the stated one of preventing them from falling into Soviet hands, was to accelerate American programs in areas where Germany had shown an advantage: rocketry, jet aviation, control electronics, guided weaponry, and synthetic materials. Peenemünde, the cradle of the V-2, had been designated by all powers as a priority target. When Soviet troops arrived there on the 5th of May of 1945, they found the installations empty of key personnel and crucial documentation. During March and April, Werner von Braun and approximately 500 members of his team had evacuated towards the south following direct orders from the German High Command, aware that Soviet capture could be politically unfavorable. They transported with them boxes containing 14 tons of technical documents, engine plans, turbopump specifications, flight test records, ballistic calculations, and metallurgical studies. The material was hidden in a mine near Goslar. A few hours after the Nazi collapse, Magnus von Braun took the risk of crossing the lines and contacting American troops to deliver the entire group of specialists along with the location of the technical archive. Meanwhile, another key point, Mittelwerk, the underground V-2 production plant, was located in the area that, according to international agreements, should have been under Soviet control. However, the United States troops arrived first. Technical teams roamed for weeks through the tunnels, still filled with machinery and rockets in different stages of assembly. Approximately 100 complete V-2s were identified, in addition to large quantities of spare parts and functional assembly lines. The United States decision was immediate: evacuate all the material before the Soviet arrival. Major John T. Hamill coordinated the systematic transfer of rockets, engines, testing equipment, and documentation. In total, about 300 loaded rail cars were sent to the west between May and June. When the area came under Soviet hands in July, the complex was practically devoid of valuable elements. The Soviet Union subsequently carried out its own systematic operation of technical extraction. Operation Osoaviakim, conducted the night of the 21st to the 22nd of October 1946, consisted of the forcible transfer of about 2,200 German specialists and their families from the Soviet zone of occupation. The deported included experts in rocketry, engines, metallurgy, optics, military electronics, and navigation. Among them was Helmut Gröttrup, deeply familiar with the V2 guidance system and production organization. These specialists were relocated to Soviet research centers, where they worked for years under strict supervision, although with access to substantial resources. Their contribution significantly accelerated the Soviet missile programs during the second half of the 1940s. The United Kingdom, lacking the logistical muscle of the United States or the territorial reach of the Soviets, focused on the technical exploitation of what was already in its possession. Operation Backfire, carried out in the autumn of 1945, consisted of the reconstruction and launch of several V2s using captured components and German personnel. The British objective was to develop complete documentation of the system, methods of filling cryogenic fuels, verification of turbine pumps, mixture regulation, launch sequences, and the structure of the guidance system. The data was recorded meticulously and was partially shared with the United States, although each power also maintained its own lines of research. In the United States, the integration of von Braun's group began in Fort Bliss, Texas, with access to White Sands Proving Ground, one of the few places suitable for launching large rockets. The captured V2s initially served for atmospheric experiments, ultraviolet radiation research, altitude temperature measurements, and telemetry tests. Between 1946 and 1952, about 70 V2s were launched from White Sands. This program allowed American engineers to gain first-hand experience in turbopumps, cryogenic valves, liquid propellant combustion, and pressurized structures. Over time, the available German components decreased. Starting in 1948, the United States began to manufacture its own models based on the captured designs, with entirely domestic production by 1950. The Redstone tactical missile, developed in the late 1950s, was in essence an increased and perfected V2. The Soviet Union replicated an equivalent process. After the arrival of technical documentation from Peenemünde and Mittelwerk, along with the direct contribution of the deported teams, the Soviet industry produced the R1, a functional copy of the V2. The R2, with increased range, incorporated structural and stability improvements also derived from German analyses. From these models, the Soviet program progressed towards the R5 and finally the R7 Semyorka, the first operational intercontinental ballistic missile, launched in August of 1957. This same vehicle placed Sputnik 1 in orbit, demonstrating that Soviet rocketry had surpassed the American in the early context of the Cold War. The technological transfer was not limited to rocketry. In jet aviation, the study of Jumo 004 and BMW 003 engines provided Allied engineers with crucial information about axial compressors, tubular combustion chambers, and materials resistant to high temperatures. The Soviets produced the RD-10, an almost exact copy of the Jumo 004, and used it in early fighter prototypes. In the United States and the United Kingdom, German research in high-speed airfoils was decisive. German wind tunnel tests had clearly documented the advantage of swept wings in transonic conditions, knowledge that was just being independently developed in other countries. This material directly influenced the design of the American F-86 Sabre and the Soviet MiG-15. The aerial confrontation between the two models in Korea, two aircraft that shared a theoretical origin in captured research, is one of the most visible indirect consequences of the technological transfer of the Second World War. The Ho-229, the flying wing of the Horten brothers, was also captured. Although the prototype never flew in a fully operational version, its geometry revealed unusually low radar scattering properties. During the 1980s, engineers of the B-2 bomber program studied the Ho-229 preserved in the United States to understand the relationship between geometry, materials, and radar signature. Although the B-2 is very far technically from the German design, the conceptual continuity is evident. Signature reduction, as a deliberate objective, found an early experimental basis in German studies. In the naval field, the Type 21 submarines perhaps represented the clearest conceptual leap. Their hydrodynamic hull design optimized for submerged navigation, their high-capacity batteries, and their functional snorkel anticipated the post-war submarine paradigm. The United States, United Kingdom, and the Soviet Union meticulously studied the captured specimens. The Guppy, Whiskey, Zulu, and Porpoise classes emerged directly from this model. Even when nuclear submarines dominated the naval scene, the diesel-electric submarines operated by many navies until the end of the 20th century retained the technical approach of the Type 21. The study of German electronic and control systems also had a profound impact. The Würzburg and Freya radars, the radio-guided missile systems like the H's 293 and the Fritz X, and the first active infrared sights were analyzed and adapted. Fundamental concepts such as command guidance, gyroscopic stabilization, and radio telemetry were incorporated into Western missile systems of the 50s. German optical companies like Zeiss and Leitz provided technology for stabilized sights, rangefinders, and night vision devices that would influence post-war armored vehicles and aircraft. In computing, the Allied forces captured Z machines of Konrad Zuse, especially the Z4. Although their influence was limited by their relative isolation during the war, Zuse's architectures showed an early transition towards fully automatic programmable computing. The Z4 operated in Zurich until 1955, providing one of the first digital computing nodes in Europe. By 1950, the technological transfer resulting from the German defeat was largely completed. The captured specialists had been reassigned, the relevant facilities had been dismantled or absorbed by new national infrastructures. The captured systems had been evaluated, copied, or replaced by own developments. What had begun as a race to secure advanced weapons was transformed into the technical foundation of ballistic missile programs, supersonic aviation, modern submarines, and electronic technologies that would define global military strategy in the following decades. The technological legacy of the Third Reich, reinterpreted and expanded by the victorious powers, directly shaped the initial stage of the Cold War and marked the starting point of the strategic systems that would characterize the rest of the 20th century.